Just 3 days ago, the European Space Agency shared what they called the clearest pictures yet of 3I Atlas. This is the space object from outside our solar system that has fascinated and scared people all over the world. Billions of dollars went into space technology. 7 spacecraft orbiting Mars were ready for a once-in-a-lifetime photo. So, what did we see? It was just a blurry white dot. It looked like someone sneezed on the camera lens. Soon after, social media exploded, not with wonder, but with anger. Even amateur astronomers, using telescopes in their backyards, were taking clearer pictures of comets millions of miles farther away. But NASA, with its Mars Reconnaissance Orbiter, which has the most powerful camera ever sent to another planet, has said nothing at all. The excuse about a government shutdown is getting old. This is especially true when you see that Chinese and UAE spacecraft are also strangely silent. By the time you hear this, 3I Atlas will be less than a week from disappearing behind the sun. It will be hidden from every telescope on Earth during what should be its most active time. If Harvard physicist Avi Loeb is right, what happens next could change everything we thought we knew about what is possible in our universe. If this mystery fascinates you as much as it does me, please hit the like button and subscribe. That way, you'll stay updated as this story happens. Tell me in the comments where you are listening from, what time it is there, and if you think we are being told the complete truth about 3I Atlas. If you want to help our community grow, please share this on X, Facebook, Reddit, or your favourite messaging app. Thank you for always supporting us. First, let's talk about the pictures that caused so much uproar online. This is the story of the photo drop that broke the internet. October 7th and 8th, 2025 will be remembered as the time when the space community finally lost its patience. For months, we had been getting ready for this. 3I Atlas is only the 3rd object from outside our solar system ever found passing through our solar system. It was making its closest approach to Mars. 7 different spacecraft from 4 space agencies were positioned to capture amazing new pictures. The excitement was huge. Scientists promised us clear images, answers, and maybe even proof of what this object actually is. And then the images were released. The European Space Agency's ExoMars Trace Gas Orbiter was positioned just 30 million km from 3I Atlas. This was during its closest approach on October 3rd. The orbiter released a series of pictures that can only be called very disappointing. It was a blurry white dot moving slowly across a field of stars. There was no detail, no shape, nothing that would help us understand if we were looking at a normal comet or something much stranger. The angry reactions were immediate and fierce. Astronomy Vibes, a popular space account on X, posted a side-by-side comparison that became very popular within hours. On one side there was a clear, detailed picture of Comet Lemon. An amateur astrophotographer took it with a simple mirrorless camera. On the other side was the ESA's picture of 3I Atlas. The caption said, "If a simple mirrorless camera can catch Comet Lemon, why can't NASA capture 3I Atlas passing close to Mars?" That post currently has over 40,000 reposts and counting. But it was the next post that really upset people. Billions in funding, and this is the best photo they've got. Looks more like a weather balloon in a foggy backyard. To understand why people are so angry, you need to know what we expected versus what we got. The CASIS camera on board the ExoMars Trace Gas Orbiter can see very small details. At 30 million kilometers, this means each pixel covers 340 kilometers. For comparison, the solid center of 3I Atlas is estimated to be between 5 and 46 kilometers wide. This means the entire solid core of this object would take up, at best, only a tiny part of a single pixel in these pictures. But here's what makes it interesting. The ESA knew this beforehand. They knew their cameras were made to photograph the bright surface of Mars from just a few hundred kilometers away. They were not made for faint objects tens of millions of kilometers away. Nick Thomas, the lead scientist for the CASIS camera, even admitted this in the official statement. He said, "This was a very challenging observation for the instrument. The comet is around 10,000 to 100,000 times fainter than our usual target. So, why release pictures they knew would not be good enough? Why build up expectations for months, only to deliver something that gives no new information?" The official story is that they released what they had. They said these were the best possible pictures from the equipment available, but the timing feels planned, almost like a way to release pressure. Give people something, anything, to look at while the real information stays hidden. Because make no mistake, there are better pictures, much better pictures, and they are being held back. Now, we will explore what became the missing crown jewel in this mystery. While the ESA was releasing blurry dots, NASA's Mars Reconnaissance Orbiter was capturing something completely different. The HiRISE camera, short for High Resolution Imaging Science Experiment, is the most powerful camera ever sent to another planet. It is so precise that from orbit around Mars, it can see objects the size of a kitchen table on the Martian surface. When 3i Atlas made its closest approach to Mars on October 3rd, HiRISE had a resolution of about 30 km per pixel at the object's distance. That is more than 10 times better than what the ESA cameras achieved. If there is any shape, any unusual features, anything that does not fit the idea of a natural comet, HiRISE would have seen it. Avi Loeb, the Harvard physicist who has been tracking 3i Atlas since it was found, said it clearly in his latest blog post. He wrote, "The brightest pixel in the HiRISE image will provide the best information yet on the area of 3i Atlas. We are all hoping that the HiRISE team will release their images as soon as possible." That was written on October 7th. It is now October 8th. Still nothing. The official explanation is the United States government shutdown. Over 15,000 NASA employees, more than 80% of the agency's workers, have been temporarily sent home. NASA's website is not being updated. Public messages have stopped. It is a government standstill at the worst possible moment. But here is what does not make sense. The ESA released their images. They are a European agency, completely unaffected by American political problems. China's Tianwen-1 orbiter was also set up to observe 3i Atlas with its moderate resolution imaging camera. Also silent. The UAE's Hope orbiter, with the Emirates Exploration Imager, also had a clear shot. Nothing. Multiple space agencies, multiple independent governments with completely separate ways of working and different goals, are all at the same time unable or unwilling to release their best information on the most scientifically important object to visit our solar system in years. This pattern is hard to ignore. Social media is full of theories. Some say there is a secret agreement. Others say something was seen that needs careful review before being shown to the public. The people who believe in bigger conspiracies suggest the images show something so strange that releasing them without proper explanation would cause widespread panic. That last theory sounds crazy until you remember what has been happening over the past week with observations from amateur astronomers. Because while the professional space agencies have been quiet with their information, backyard astronomers have been taking pictures that raise more questions than they answer. In our third section, we'll look at when amateurs see what professionals won't show. On October 3rd, the exact day 3i Atlas made its closest approach to Mars, a Portuguese amateur astronomer, using the name Dobsonian Power, uploaded a picture that quickly became very popular. Using nothing more than a solar telescope from his backyard and some strong digital adjustments, he captured what looks like an angled structure inside 3i Atlas. There were dark geometric shapes, parts sticking out that do not match the usual soft glow of a comet's cloud. The caption he added was simple, but it hinted at something important. What on earth is it? Within 6 hours, the image had been shared across every major astronomy forum, subreddit, and social media site. The reactions split into two groups almost instantly. One group saw clear proof of man-made structures. They believed it showed that 3i Atlas is not what mainstream science claims it to be. The other group dismissed it as a classic case of pareidolia. This is the human tendency to see patterns where there are none. They said it was made worse by errors from using the wrong equipment and strong image processing. Those who argued against the image had strong technical points. Solar telescopes use special filters designed to observe the sun's extreme brightness. They are not meant for faint, deep space objects moving at high speeds between stars. The equipment simply was not built for this kind of observation. If you add strong digital enhancements to make up for the inadequate setup, you're basically asking a computer program to invent details that are not really there. It is like trying to make a blurry photo clearer until you start seeing faces in the noise. But here is where the story gets more complex. Dobsonian Power is not just some random internet conspiracy theorist with a cheap telescope and too much imagination. He is a respected amateur astronomer who has been sharing real astrophotography work for over 10 years. His YouTube channel shows careful details of his equipment, his methods, and how he processes his images. This is not someone trying to create fake evidence for clicks. And when asked about the strange shapes in his 3i Atlas image, he did not double down with wild claims. Instead, he admitted he was unsure. He promised to try again when the object becomes visible from Earth in early November after passing behind the Sun. His response was calm, scientific, and appropriately careful. This makes the reaction to his image even more telling. Within 24 hours, many websites published articles specifically trying to disprove his picture. Headlines read, "Amateur telescope captures strange three-eye atlas image. Here's why it's not what it seems." The timing felt coordinated. The tone felt defensive. It was as if someone needed to quickly establish the idea that nothing unusual had been photographed. They wanted to say that any apparent strange features were just technical errors before the image could get too much attention. And then the enhancement wars began. Users across Reddit, Twitter, and various conspiracy forums started downloading the original ESA images. They ran them through their own image processing programs. Some used standard astronomical image stacking techniques. Others used AI tools made for making low-resolution photos better. A few went full chaos mode with machine learning programs trained to rebuild fine details from limited information. The results were very different. Some showed nothing but slightly clearer versions of the same blurry dot. Others revealed what appeared to be distinct geometric patterns, edges, and structures that seemed too regular to be natural ice and rock. The problem is that once you start heavily processing an image, especially with AI tools, you are no longer looking at what is actually there. You're looking at what a computer program thinks should be there, based on the information it was trained on. If you train an AI on thousands of images of spacecraft, and then ask it to make a blurry dot clearer, it might very well invent spacecraft-like details because that is what it has learned to recognize. It is a scientific dead end disguised as clarity. But the spread of these enhanced images had an unexpected effect. They made the situation so confusing that it became almost impossible to tell the difference between real amateur observations and outright fakes. Within 48 hours of the ESA photo release, there were dozens of supposedly enhanced versions circulating online. Some showed metallic surfaces, others depicted what looked like solar panels or antennas or arrays. A few even included running lights and visible thrusters. Most were clearly fake digital art created by people with too much time and too much Photoshop skill. But mixed in with all the fake images were a handful that felt different. They were more subtle, less attention-grabbing. These images showed just enough unusual regularity to make you wonder if something real was being hidden by the flood of obvious hoaxes. Our fourth part dives into the 4chan leak that won't go away. On October 4th, an anonymous user on 4chan's paranormal board posted what they claimed was secret information about Three-Eye Atlas. The post was simply titled ESA Data Leak. It began with a claim of being an insider that sounded specific enough to be true, but vague enough to keep the person anonymous. The poster wrote, "I am a doctoral researcher working with the European Space Agency with continuous access to the combined observational data of Three-Eye Atlas." Internet leaks are very common. Most are easily dismissed as made-up stories or simply trolling, but this one was different. The amount of technical detail was unsettling. The poster did not make wild claims about alien invasions or secret military operations. Instead, they described a series of specific strange observations. If these were true, they would completely change what we understand about what Three-Eye Atlas actually is. The first strange observation was chemical impossibility. According to the post, tests showed that Three-Eye Atlas is releasing about 100 kg of nickel gas per second, but almost no iron gas. In normal star and planet chemistry, nickel and iron are always found together. They form together in supernova explosions. They travel together through space between stars, and they appear together in comets and asteroids. Finding a lot of nickel with almost no iron is like finding smoke without fire. It goes against basic ideas about how matter behaves in natural space environments. The second strange observation was thermal contradiction. The object is releasing huge amounts of gas and dust. This is a common sign of an active comet being heated by the sun. But infrared observations show it remains cold, much colder than it should be given how much gas it is releasing and how close it is to the sun's radiation. The poster compared it to watching someone sweat a lot in a freezer. The physics does not match what they observed. The third strange observation was trajectory precision. The post mentioned what Avi Loeb has been saying publicly, that Three-Eye Atlas arrived with an orbit that was only 4.89 degrees off from Earth's flat plane around the Sun. But the 4chan poster added something Loeb did not emphasize. The path is not just unusual, it is a perfectly straight shot from the direction of the galactic core. There is no wobbling, no change in direction, no signs of being pulled by nearby stars during its millions or billions of years travelling through space as if it was aimed. Then came the part that changed this from interesting speculation to something darker. The poster claimed the object fits the description of what they called a post-biological entity. It was not a natural comet, not normal spacecraft, but something in between. They described it as having a 3-phase particle engine with an estimated power output of 75 megawatts. It was continuously sending out an active signal, and in their words, probing our solar system. The post ended with a theoretical idea. The poster suggested 3i Atlas might be a macroscopic quantum object, specifically something called a cue ball. This is a strange theoretical idea from particle physics. It is a type of special wave that could theoretically exist at sizes much larger than tiny subatomic particles. If stable, a cue ball could have properties that seem impossible with normal physics. It could be incredibly dense while appearing spread out. It could absorb and move energy instantly across its entire structure, explaining why it is so cold despite releasing gas. It could even explain the nickel without iron problem if the cue ball's internal quantum state mainly produces certain types of atoms. Within 18 hours, the post had been screenshotted and shared across Reddit, Twitter, and dedicated UFO research forums. The conspiracy subreddit thread discussing it gathered over 2,000 comments before moderators locked it. They said it broke rules against unverified claims, but locking the thread did not stop the conversation. It just moved it to other platforms. It broke into dozens of separate discussions, each pulling the original post in different ways. Some focused on the strange chemicals, others zoomed in on the cue ball idea. A few started connecting it to earlier claims about 3i Atlas possibly being the source of the 1977 WOW signal. Next, we face the 50,000-kilometre question. On October 4th, NASA's Perseverance rover was in Jezero crater on the surface of Mars. It captured something in the night sky above. The image from its right navigation camera showed a long streak of light, roughly 4 times longer than it was wide. At first glance, it looked like a normal long-exposure picture of a moving object. Comets and asteroids often appear smeared in images when the camera tracks stars instead of the object itself. This is normal. Except the math did not work out that way. When people started calculating the apparent size of the streak based on Perseverance's known camera details and the distance to 3i Atlas at the time, they arrived at a troubling number, 50,000 km long. That is not a comet's core. That is not even a comet with a tail. That is something else entirely. For comparison, Earth's diameter is less than 13,000 km. If this streak showed the actual physical size of 3i Atlas, we were looking at an object nearly 4 times wider than our entire planet. Social media exploded with theories. Was 3i Atlas actually a massive cylindrical craft? Had it been hiding its true size and shape all this time behind a fuzzy cloud of gas and dust? The timing felt important. This image appeared just 1 day after the Mars flyby, right when all the professional space agencies suddenly went quiet. Some saw it as proof that something very strange had been photographed. Something that could not be easily explained away. The theories became so widespread that Representative Anna Paulina Luna, a member of Congress known for her interest in unexplained aerial phenomena, directly asked Avi Loeb for his thoughts. Think about that for a moment. A sitting member of the United States House of Representatives felt it necessary to contact a Harvard physicist about a photograph from Mars. That is not normal procedure. That suggests someone in official government channels was concerned enough to want an expert opinion outside the usual NASA communication channels. Loeb's response was thorough and at first glance comforting. He calculated that the Perseverance navigation camera has a specific angular resolution. At the distance of 3i Atlas when the image was taken, about 38 million kilometers, that translates to about 12,500 kilometers per pixel. The streak in the image covers roughly 4 pixels, which gives you that 50,000 kilometer length. But Loeb argued this was an error from combining images. The streak was not showing the actual size of 3i Atlas. It was showing the path the object took across the Martian sky during a long exposure time, likely around 10 minutes of combined photos. His reasoning was strong. Mars orbits the Sun at 24 kilometers. 3i Atlas was travelling at 67 kilometers relative to the Sun in the opposite direction. This gives it a relative speed of over 90 kilometers compared to Mars. Over 10 minutes, That is exactly 54,000 km of travel, perfectly matching the observed streak length. The shape was not the object itself, it was the object's movement spread out over time. Case closed, right? The cylinder theory disproved by basic physics and careful math. Except Loeb included one sentence in his analysis that conspiracy theorists clung to like a lifeline. He wrote, "If the NavCam images represent single snapshots with an exposure time below 3.2, 28 seconds, then the brightness and angular length of the observed source imply that it is not 3i Atlas. In that case, the source might be much closer to the camera, capable of being smeared into an elongated image with a smaller spatial size and a smaller speed. Wait, if these are single-frame captures, then what? Perseverance photographed was not 3i Atlas at all. It was something else, something closer to Mars. That added condition opened a door that no amount of later explanation could fully close. Because NASA has not confirmed whether the image is a combined image or a single frame, they have not released the detailed information about the image, they have not provided the exposure time or the number of combined images. The government shutdown excuse applies here too. No staff to process requests, no one available to confirm basic technical details about how the image was captured. This brings us to 48 years of silence. On August 15, 1977, Ohio State University's Big Ear radio telescope picked up a 72-second burst of radio energy. It was so unusual, so perfectly structured, that astronomer Jerry Eamon circled it on the printout and wrote one word in red pen: "Wow!" For almost 5 decades, that signal has been one of the biggest mysteries in the search for alien life. It came from the direction of Sagittarius, near the constellation's densest star fields. It was very focused, at one specific frequency, and it has never happened again. Hundreds of follow-up observations, thousands of hours of listening time pointed at the same region of sky. Nothing. Just that one burst 48 years ago, and then complete silence. Until Avi Loeb ran the numbers on 3i Atlas. He calculated where the object was on August 12, 1977, just 3 days before the WOW signal was detected. The answer: approximately 600 astronomical units from Earth, which is about 600 times the distance between Earth and the Sun. But more importantly, he calculated what direction 3i Atlas was coming from at that time. Right ascension, 19 hours 40 minutes, declination 19 degrees. The WOW signal came from right ascension 19 hours, 25 minutes, declination negative 27 degrees. The two directions are separated by about 9 degrees. In the vastness of space, with random objects coming from literally any possible direction, the chance of this alignment is about 0.6%. Not impossible, but very suspicious. Loeb did not stop there. He asked the next logical question. If 3i Atlas sent the WOW signal from 600 astronomical units away, how powerful would the transmitter need to be? The math is straightforward. The detected intensity was between 54 and 212 Jansky, across a 10 kHz bandwidth. At 600 AU distance, that means the transmitter would need to put out between half, a gigawatt, and 2 gigawatts of power. For comparison, a typical nuclear reactor on Earth produces about 1 gigawatt. So, we are talking about energy levels like a nuclear power plant, focused into a narrow radio beam. Not impossible for an advanced civilization. Actually, quite reasonable if you're trying to send a detectable signal across interstellar distances without wasting energy by broadcasting in all directions. There is another detail that makes the connection harder to ignore. The WOW signal was observed at a frequency of 1,424 seconds, shifted slightly towards Earth by about 10 kilometers, compared to the hydrogen line. That shift towards blue indicates the source was moving toward us. 3i Atlas is currently approaching the Sun at about 60 kilometers. Loeb suggests that if this object can move on its own, it could have been moving slower in 1977. Then, it sped up after detecting planets in our solar system that could support life. This could be a reconnaissance pulse, a radar scan checking for signs of technological civilization before coming closer. Here is what makes this entire connection so frustrating. It would be very easy to check. Point a radio telescope at 3i Atlas, listen at the hydrogen line frequency. If it is transmitting, we will know within hours. If it is silent, the WOW signal connection is probably just a coincidence, a simple test, a clear answer. And yet, As Loeb noted in his latest blog post, not a single radio telescope has reported information on 3I Atlas. The Very Large Array has not looked. The Arecibo telescope is destroyed. The Green Bank telescope has not published observations. Even SETI, the organisation specifically dedicated to finding alien signals, has not publicly announced any monitoring efforts. The silence from the radio astronomy community is deafening. Now, let's discuss the path that shouldn't exist. Imagine throwing a dart at a globe from across a room while blindfolded. Now imagine that dart not only hits the globe but lands within a few degrees of the equator. That is roughly how unlikely it is when we look at how 3I Atlas entered our solar system. Objects coming from space between stars can arrive from literally any direction. They should be spread randomly across the sky, coming in at all possible angles. And yet, 3I Atlas arrived with an orbital path that was only 4.89 degrees off from Earth's flat plane around the Sun, less than 5 degrees. That puts it in less than 1% of possible arrival angles. Avi Loeb has been repeating this point in every interview, every blog post, every public statement since July. The path is unusual. It is not just strange, it is statistically very unlikely for a random object from interstellar space. To understand why, you need to think about how objects move through the galaxy. Stars in the Milky Way disk orbit the galactic center with some average speed, but they also have random motions up and down, side to side, like bees swarming around a hive. That randomness means objects shot out from other star systems should arrive at our solar system from all directions with roughly equal chance. There is no special direction, no cosmic highway that guides interstellar visitors into our solar system's main plane. And before someone suggests that maybe objects from the Milky Way disk naturally arrive at shallow angles, Loeb addressed that too. The galactic disk itself is tilted about 60 degrees compared to our solar system's flat plane. 60 degrees! That is more than 10 times larger than the tilt of 3I Atlas. If this object came from a typical star system in the galactic disk and was ejected randomly, we would expect it to arrive at a steep angle, not a shallow one. The alignment is the opposite of what the galaxy's shape would predict. Compare 3I Atlas to the only other interstellar objects we have found. Oumuamua, discovered in 2017, arrived with a tilt of 123 degrees, wildly angled, coming in from above the solar system's plane. Tui Borisov, seen in 2019, had a tilt of 44 degrees. Still steep, still consistent with a random arrival from space between stars. Both of those objects behaved exactly as expected for natural interstellar visitors. 3I Atlas is the exception, the strange one, the one that does not fit the pattern. Loeb calculated the chance of this alignment, assuming random directions, is less than 1%. Some of his colleagues argued back, suggesting maybe his statistics were too cautious. Maybe the true chance is closer to 5 or 10% when you consider various ways we choose what to observe and how we might be biased. Fine. Even at 10%, you're still looking at something that should only happen once in every 10 interstellar objects we find, and we have only found 3. The odds of the third one being the rare exception, rather than the rule, are not in favour of coincidence. Now add that to everything else. The WOW signal alignment also has less than a 1% chance. The strange chemicals with nickel but no iron, the unexpected coldness, the missing high-resolution images from multiple space agencies, the government shutdown happening exactly when we need NASA most. Any single one of these things could be explained away. Coincidence, measurement error, government inefficiency. But when you start adding these strange things together, when you start multiplying small probabilities, the combined unlikelihood becomes harder to ignore. There is a principle in statistics called the prosecutor's fallacy. It is the mistake of treating several independent low-probability events as if they are connected when they are actually just random coincidences that happen to occur together. If you flip a coin enough times, eventually you will get 10 heads in a row. It does not mean the coin is rigged, it just means you flipped it enough times for unlikely sequences to occur. Skeptics will argue that is what we are seeing with 3I Atlas, a natural comet that happens to have several unusual but ultimately explainable properties that coincidentally appeared together in the same object. Unlikely, sure, but not impossible. The counter-argument is equally strong. If something walks like a duck, quacks like a duck, swims like a duck, and has duck DNA, At some point you have to consider the possibility that it might actually be a duck. Or in this case, if an object arrives on a statistically unlikely path, shows chemical signs that do not match natural processes, matches a 48-year-old unexplained radio signal, and causes multiple governments to hold back their best imaging, data. Maybe it is worth seriously thinking that we are not looking at a random chunk of ice and rock from another star system. Our 8th section looks at when questions become dangerous. Something strange started happening around October 5th. Users across many platforms began reporting that their posts about 3i Atlas were disappearing. They were not being flagged or marked as wrong information, they were actually vanishing. A Reddit user shared how they posted a detailed discussion analysing the strange chemicals from the alleged ESA leak. The discussion gained attention, getting hundreds of upvotes and dozens of comments within 2 hours. Then it was gone, not removed with an explanation from a moderator, just deleted from existence. When the user tried to repost, the submission would not go through. They were secretly blocked without notice or explanation. On Twitter, now X, several accounts noticed similar patterns. Astronomy Vibes, the account that became popular for criticising the ESA photos, reported significant drops in how many people saw their posts after October 7th. Posts that would normally reach tens of thousands of people were suddenly stopping at a few hundred views. There were no official restrictions, no warning messages, just a hidden blocking by the computer programs. It was quiet enough to be denied, but strong enough to be effective. Other creators in the space astronomy community noticed the same thing. Videos about 3i Atlas that would usually do well were getting only a small part of their normal reach. YouTube presented a different problem. Creators who posted analysis videos guessing about 3i Atlas started getting notices that their videos would not earn money. The stated reason was different each time. Some were flagged for talking about sensitive topics without proper context. Others were called potentially misleading content about scientific matters. A few got hit with the vague but worrying label of content that may not be suitable for all advertisers. The pattern was clear. You could make a video saying 3i Atlas is definitely just a comet, and mainstream science understands it. That was fine, earned money, and was promoted. But if you suggested there might be strange things worth investigating, suddenly your video became unfriendly to advertisers. Facebook's approach was the most direct. The platform's fact-checking system, run by outside verification organizations, started strongly labeling 3i Atlas content. Posts sharing the 4chan leak were given missing context warnings. Claims about the unusual path were flagged as partly false, even when the posts were just quoting Avi Loeb's published calculations word for word. The fact-check articles offered reassurance: space agencies confirm no threat from interstellar comet. Experts say unusual features likely natural processes. The hidden message was clear: don't worry, don't guess, trust the authorities, move along. The timing felt coordinated. This increased within 48 hours of the ESA photo release. This was when public frustration was highest over the lack of good images. It is the kind of pattern that makes conspiracy theorists feel they are right and makes skeptics roll their eyes at too much paranoia. Because here is the thing, social media platforms block content all the time. Computer programs change, engagement goes up and down, fact-checkers flag wrong information. These are normal platform operations, not proof of coordinated censorship unless there is a pattern. Unless it is all happening at once, targeting one specific topic, right at the moment when public interest is highest and official answers are most absent. Some creators started using secret language to avoid being blocked. Instead of 3i Atlas, they would say the visitor or the object. Instead of alien or extraterrestrial, they would use non-terrestrial or anomalous. It was like watching people create a new way of talking to discuss something the platforms did not want discussed openly. This is known as the Streisand effect in real time. The more the content was blocked, the more people assumed there was something worth hiding. The more aggressively fact-checkers pushed back, the less people trusted the official story. Every attempt to control the conversation just increased the suspicion that the conversation needed to be controlled. In this part, we discuss the moment we can't watch. October 29th and 30th. Mark those dates. In less than 3 days from now, 3i Atlas will reach perihelion, its closest approach to the Sun. It will pass at a distance of approximately 202 million kilometers, just inside the orbit of Mars. For a natural comet, this is the moment of truth. The intense sunlight at that distance should cause a dramatic release of gas, possibly even breaking apart. We have seen it happen before. Comets get close to the sun, the heat becomes too much, and they break into pieces. It is spectacular when it happens. And if 3I Atlas is just an ordinary chunk of ice and rock from another star system, that is exactly what should occur. But here is the problem. We will not be able to see it. 3I Atlas will be on the opposite side of the Sun from Earth during its closest passage. Every telescope on our planet will be useless. The object will be lost in the Sun's glare, completely hidden from observation during what should be its most active and revealing moment. Some are calling it unfortunate timing. Others see it as suspiciously convenient. If you wanted to do something without being watched, you could not pick a better window. Avi Loeb has been clear about what happens next. In his October 3rd blog post, published on the day of the Mars flyby, he laid out two possibilities. If 3I Atlas is a natural comet, it may erupt in a flare of outgassing or break up into icy fragments soon. The sunlight will deposit gigawatts of power onto its surface. That energy has to go somewhere. For ice and rock, it goes into turning into gas, evaporating, possibly breaking the structure. But then Loeb added the other option. Alternatively, if it is technological, it may maneuver to benefit from the Sun's gravitational assist or release probes that could intercept the Earth or other planets owing to its retrograde orbit opposite in direction to the motion of the planets around the Sun. Read that again. Release probes that could intercept Earth. He's not talking about just watching anymore. He's talking about actively launching something. The retrograde orbit is key here. 3I Atlas is moving in the opposite direction to how planets orbit the Sun. That means any probe it releases does not have to fight against planetary motion to reach us. It can simply drop into a path that will intercept Earth, and orbital mechanics will do the rest. From behind the Sun, hidden from our view, it would be simple to launch something toward Earth that would not be detected until it was already close. Loeb went further. He wrote, "When you look at the Sun in the coming weeks, keep in mind that 3I Atlas is passing behind it. If 3I Atlas will maneuver towards Earth, when it reappears on the other side of the Sun, the financial markets may crash. Financial markets may crash. That is not a figure of speech. That is not an exaggeration. He is suggesting that if this object shows it has technology, if it changes course toward Earth after passing the Sun, the economic and social effects would be immediate and severe. Stock markets react to uncertainty. The uncertainty of a potentially hostile interstellar object actively changing its path toward our planet would be an extreme level of uncertainty. The timing of everything adds to the tension. The government shutdown means NASA is offline during the important observation time. The best images from the Mars flyby are still not released. Amateur astronomers cannot observe the object for the next month because it is behind the Sun. Radio telescopes have not checked for transmissions. We are flying blind into the most important moment of this entire encounter, and whether through mistakes or on purpose, we have created a situation where we will not know what 3I Atlas does at its closest approach to the Sun until it has already done it. There is one group watching. The Galileo project, led by Loeb himself, runs 3 observatories, one in Massachusetts, one in Pennsylvania, one in Nevada. They have high-resolution cameras, infrared sensors, and radio receivers designed specifically to detect unusual aerial phenomena. During late October and early November, all 3 observatories will be operating at their fullest, watching the skies for anything strange. If 3I Atlas releases probes, if there is increased UAP activity linked to its passage near the Sun, the Galileo instruments might catch it. Might is the key word. 3 observatories covering a small part of Earth's sky. If something comes and avoids those specific observation zones, we will miss it entirely. So, what comes after? This is what comes after. Early November. That is when 3I Atlas will emerge from behind the Sun and become visible again from Earth. Ground-based telescopes will be able to track it once more. We will see whether it survived its closest approach to the Sun intact or broke apart under the Sun's heat. We will measure its path to see if any course corrections happened. And we will finally know whether the past 4 months of guessing, conspiracy theories, and unanswered questions were justified or just mass panic over a completely natural visitor from space. If 3I Atlas emerges on the same path it entered with, if it shows clear signs of breaking apart or increased gas release, consistent with the sun's heating, if it behaves exactly like 2I Borisov did during its approach to the sun in 2019, then the mystery is essentially solved. A natural comet, unusual chemistry, sure. A statistically unlikely path, granted. But ultimately just an icy remnant from another star system passing through ours. The WOW signal connection becomes a coincidence. The 4chan leak becomes a made-up story. The missing NASA images become bureaucratic delays during a government shutdown. Everything slots back into the comfortable framework where interstellar objects are interesting but not alarming. But if it does not, if 3I Atlas emerges with a changed path, if it shows even subtle course corrections that cannot be explained by gas pushing it, if radio telescopes finally point at it and detect structured transmissions, if the NASA images eventually appear and show geometric structures that should not exist on a natural object, then we are in completely unknown territory. Not just scientifically, but socially, politically, economically. Every assumption about our place in the universe gets challenged. Every government's response to the question of contact with aliens gets tested in real time. Avi Loeb created something he calls the Loeb scale. It is a ranking system for how likely an object is to be man-made and how much of a potential threat it represents. Rank 1 means almost certainly natural with interesting but explainable strange features. Rank 10 means definitely man-made with shown hostile intent and the ability to reach Earth. He stated publicly that he will not rank 3I Atlas lower than a 2. Even in the best case, the strange features are too consistent, too many, too connected. A 2 means probably natural, but with enough unexplained features to need serious investigation. It means we cannot definitively rule out a man-made origin without more information. That is where we are right now, stuck between a probable natural object and a possible technological artifact, waiting for November, waiting for the high-resolution images that may never come, waiting for radio observations that have not happened, waiting for 3I Atlas to either continue on its long, open path out of the solar system, never to be seen again, or to do something that forces us to face the reality that we are not alone and we are not ready. The ESA has announced that their Jupiter Icy Moons Explorer spacecraft JUICE will observe 3I Atlas between November 2nd and 25th using various instruments. This will happen just after its closest approach to the Sun, when the object should be most active. The data will not be available until February 2026 due to delays in communication and processing time. 7 months of waiting for images that were captured in November. 7 months of not knowing whether the increased activity JUICE observes is normal comet gas release or something else entirely. 7 months of wondering whether that blurry dot the ESA showed us in October was really the best they could do, or whether they are carefully managing a big reveal they do not know how to share. Whatever 3I Atlas is, whatever it does in the coming weeks, the discussions around it have already shown something important about where we are as a civilization. We do not trust our institutions to tell us the truth about something this important. We do not believe the official reassurances. We see patterns in the timing of shutdowns and data delays that may or may not be real. We are ready for conspiracy theories because we have learned, sometimes the hard way, that a conspiracy is not always just a theory. Sometimes it is just early reporting on what later becomes proven fact. Now, let's turn our attention to the invisible visitor. On October the 1st, 2025, something the size of a giraffe passed between Earth and our satellites. It came closer to our planet than the International Space Station orbits. We had no idea it was coming. By the time astronomers saw it, asteroid 2025 TF had already gone. It slipped back into the darkness of space like a shadow that forgot to announce itself. Think about that for a moment. We live in a time when we can photograph distant galaxies forming billions of years ago, yet a rock close enough to practically brush our atmosphere went completely unnoticed until it was already behind us. If you find that as unsettling and fascinating as I do, consider liking and subscribing to stay updated on these cosmic close calls and the mysteries happening above us. Tell me in the comments where you're listening from, what time it is there, and whether you think we should be more worried or more amazed by how much we still miss in the night sky. And if you want to help our community grow, share these videos on X, Facebook, Reddit, or your messenger. Thank you for always having our back. The asteroid measured somewhere between 1 and 3 meters wide. It was small enough that if it had actually entered our atmosphere, it would have burned up as a brilliant fireball. Nothing that would threaten cities or civilizations. But here is what keeps astronomers awake at night. If we cannot reliably detect something this close, something travelling at speeds that would cross the distance from New York to Los Angeles in less than a minute, what else might we be missing? The European Space Agency and NASA track thousands of near-Earth objects. They carefully list which ones pose the greatest risk of hitting us. To be called potentially hazardous, an asteroid must be at least 140 metres in diameter and follow an orbit that brings it within 7.5 million kilometres of Earth, roughly 20 times the distance between us and the Moon. Asteroid 2025 TF is much smaller than that size. This partly explains why it was not found earlier. Our telescopes and survey systems focus on finding the big ones, the ones that could end civilizations, the objects that could cause another extinction event if they struck at the wrong angle. But this tiny visitor reminds us that space is not empty, it is full of debris. These are ancient fragments from when our solar system was forming, pieces of broken worlds that never quite became planets. Remains of collisions that happened when Earth itself was young. Most of this material stays far away, held in stable orbits in the asteroid belt between Mars and Jupiter, or drifting in the distant Kuiper belt beyond Neptune. But gravity from large planets, like Jupiter's huge mass, or a nudge from a passing comet, can shift these orbits. This sends rocks on new paths that sometimes cross with ours. What makes 2025 TF particularly interesting is not just that it came close, but that it came close during a month when the sky seems unusually busy with visitors. Our next chapter is about the brightening wanderer. While one cosmic traveller slipped past us unnoticed, another is making a much more dramatic entrance. Comet C 2025 A6, better known as Lemon after the observatory that discovered it, is getting brighter in our October skies. Astrophotographers around the world have been taking increasingly amazing pictures as this ball of ancient ice and dust moves toward a close approach with Earth. Unlike the hidden asteroid that surprised us, Lemon has been tracked carefully since it was discovered, and right now it is just at the edge of what humans can see with their eyes. Over the next few weeks, if conditions are right and skies are dark enough, you might be able to step outside and see it yourself. It will look like a faint smudge of light with a ghostly tail stretching away from the sun. Comets are very different from asteroids. Asteroids are rocky or metallic solid chunks of material that formed in the warmer inner solar system. Comets are icy bodies that came from the cold outer parts of the solar system. They are sometimes called dirty snowballs, though that description does not fully describe them. A comet's core contains frozen water, carbon dioxide, methane and ammonia mixed with dust and organic compounds. These are the chemical building blocks of life. As a comet gets closer to the sun, sunlight warms its surface. This causes the ice to sublimate, turning directly from solid to gas without first becoming liquid. This creates the coma, a temporary atmosphere of gas and dust that can stretch for hundreds of thousands of kilometers. Solar wind and radiation push this material away from the core, forming the characteristic tail that always points away from the sun, no matter which direction the comet is travelling. Lemon is not the only comet gracing our skies this month. Another visitor, C 2025 Rost, known as Swan, slides past Earth later in October at a distance of 0.26 astronomical units. This is close enough to put on a show for those with binoculars or small telescopes. Both comets currently shine at about magnitude 6, which is right at the limit of human vision under perfect conditions. But comets are famous for being unpredictable. They can suddenly get brighter if their rotation exposes fresh ice to sunlight, or if an outburst sends a plume of material into space. They can also break apart under the stress of solar heating or gravitational forces. This creates multiple cores that each develop their own coma and tail. What draws people to watch comets, besides their beauty, is their connection to deep time. The ice in these objects formed billions of years ago in the outer solar system. It was preserved in a cosmic freezer, far from the sun's warmth. When we see a comet, we are seeing material that existed before Earth had oceans, before the moon was fully formed, before life began in whatever warm tidal pool or deep-sea vent first started self-replicating chemistry. Some scientists believe that comets delivered large amounts of water to early Earth. This happened during a period of heavy bombardment that helped fill our oceans. Others suggest that the organic molecules found in comets including amino acids, the building blocks of proteins, may have seeded our planet with the raw materials needed for life to begin. This connection between ancient comets and the origin of life brings us to another discovery that has scientists rethinking how common the ingredients for life might be across the universe. Next up, we have a nursery for moons. 625 light-years from Earth, something remarkable is happening around a young planet. The James Webb Space Telescope has captured the first direct measurements of a moon-forming disk. This is a rotating ring of gas and dust surrounding an exoplanet called PDS-70c. And within that disk, Webb detected the chemical signs that could give rise to moons: hydrogen cyanide, acetylene, benzene, propyne, ethane, carbon dioxide. All of these are carbon-rich molecules swirling in a structure that looks strangely familiar to planetary scientists who study our own solar system's history. This matters because for decades we have theorized about how moons form, but we have never actually watched it happen. Jupiter's 4 largest moons, the Galilean satellites discovered by Galileo in 1610, orbit their planet in a flat plane. This suggests they formed from a disk of material surrounding Jupiter billions of years ago, much like the planets formed from a disk around the young Sun. The 2 outermost of these moons, Ganymede and Callisto, are 50% water ice, though they likely have rocky cores of carbon or silicon beneath their frozen shells. Looking at their orbits and compositions, scientists have long believed that a circumplanetary disk once existed around Jupiter, and within that disk the raw materials for moon formation gathered and stuck together. Now, with PDS-70c, we can see a similar process unfolding in real time, although we have to remember that real time in astronomical terms is a bit misleading. The light we detect from this system left 625 years ago, when Earth was in the middle of the Renaissance and no one had yet imagined planets beyond our own solar system. But from our perspective, we are watching moon formation as it happens, and the details are fascinating. The planet itself orbits a star that is only 2 million years old. It is still collecting material from its own disk of gas and dust. This means we are seeing a system in its early stages, a planetary nursery where multiple generations of structure formation happen at the same time. What surprised researchers most was the clear chemical difference between the planet's moon-forming disk and the star's planet-forming disk. The disk around PDS-70c is rich in carbon-containing molecules, but shows no signs of water. Meanwhile, the disk around the star contains water, but lacks the carbon chemistry seen in the planet's disk. This chemical separation happened in just 2 million years. This suggests that disk chemistry changes rapidly and follows different paths depending on local conditions. Temperature, radiation levels, the presence of magnetic fields, all of these factors influence which molecules can survive and which get broken apart. The implications go beyond understanding how moons form. If we can map the chemistry of these disks in young systems, we can start to predict which exoplanets might have moons, and which of those moons might have conditions suitable for life. In our own solar system, some of the most promising places to search for life are not planets, but moons. Europa, orbiting Jupiter, likely has a liquid water ocean beneath its icy crust, kept warm by tidal heating from Jupiter's gravity. Enceladus, a small moon of Saturn, shoots geysers of liquid water into space from an underground ocean. And within those geysers, scientists have detected organic molecules. If moons around other stars form with similar characteristics, then the number of potentially habitable worlds in the galaxy increases greatly. We would need to look not just at planets in the habitable zone around their stars, but at moons around giant planets anywhere in a system. This expanding view of where life might arise connects to technologies we are developing here on Earth. Technologies that might one day help us reach these distant worlds, or at least understand them better. Let's explore the quantum leap. The United Nations has named 2025 the International Year of Quantum Science and Technology. This marks 100 years since quantum mechanics first started to be developed. It is good timing because 2025 is shaping up to be the year when quantum computing changed from a lab curiosity to something close to being practically real. In November of 2024, Microsoft and Atom Computing announced they had successfully created and linked 24 logical qubits. This is a technical achievement that marks a big step toward building quantum computers that can actually solve useful problems. To understand why this matters, we need to talk about what makes quantum computers different from the device you're using to listen to this right now. Regular computers, whether they are smartphones or supercomputers, process information using bits. These are units that represent either 0 or 1, on or off, true or false. Everything your computer does, from streaming video to running complex simulations, comes down to handling huge numbers of these binary digits at incredible speed. Quantum computers work on completely different principles. Instead of bits, they use qubits, which are quantum bits. These can exist in a mix of states, simultaneously representing 0 and 1 until they are measured. This is not just a metaphor or a trick. At the quantum scale, particles truly exist in multiple states at once. This is a result of the wave-like nature of matter as described by quantum mechanics. When you have multiple qubits in this mixed state, they can represent exponentially more information than the same number of regular bits. 2 regular bits can represent 4 possible values, 00, 01, 10, or 11, but only one at a time. 2 qubits in a mixed state can represent all 4 values simultaneously. 3 qubits can represent 8 values at once. The scaling continues very quickly, which means a quantum computer with just a few hundred qubits could theoretically perform calculations that would take regular supercomputers longer than the age of the universe. But there has always been a problem. Qubits are extremely fragile. They lose their quantum properties, a process called decoherence, when they interact with their surroundings. Changes in temperature, stray electromagnetic fields, even cosmic rays passing through the lab can cause errors. This is why quantum computers must be cooled to temperatures near absolute zero and protected from outside interference. Even then, errors build up so quickly that calculations become unreliable before you can finish them. The breakthrough that makes 2024 and 2025 so important is progress in quantum error correction. This is the ability to detect and fix these errors without destroying the quantum state you're trying to keep. Creating 24 linked logical qubits means creating qubits that have built-in error correction. This makes them much more stable and reliable than the physical qubits that make up the actual hardware. Entanglement is another quantum phenomenon that Einstein famously called spooky action at a distance. When qubits are linked, measuring the state of one instantly affects the state of the others, no matter how far apart they are. This allows quantum computers to perform certain types of calculations, like searching databases or factoring large numbers, much more efficiently than regular computers ever could. The race to build practical quantum computers is now global and very competitive. In early 2025, Japan announced a $7.4 billion investment in quantum technology. Spain committed $900 million. These investments bring total public funding for quantum research to over $10 billion. This signals that governments see quantum computing not just as a scientific curiosity, but as a key technology that could change everything from finding new drugs to cybersecurity to artificial intelligence. The private sector is equally invested. Companies like Google, IBM, and Amazon continue to push the limits of what is possible. Google has claimed its quantum processors can solve certain problems exponentially faster than classical supercomputers. IBM has planned to build a system with 200 logical qubits by 2028. Meanwhile, startups are exploring different methods, using photons instead of superconducting circuits, or trapped ions instead of solid-state devices. Each method has its own advantages and challenges. But beyond the engineering achievements, there is something almost philosophical about quantum computing that captures the imagination. These machines work based on principles that defy our everyday understanding of how reality works, and yet those principles appear to be fundamental to the universe itself. The same quantum mechanics that makes qubits possible also governs how atoms behave, the structure of molecules, and how light is given off by stars. In a way, quantum computers are allowing us to use the universe's own language to solve problems that would otherwise be impossible. One of those problems is understanding and controlling the process of nuclear fusion, which brings us to another set of breakthroughs that happened at the same time. Now, we'll talk about capturing the stars. On February 12, 2025, scientists at the West Tokamak reactor in France set a new world record. They kept extremely hot plasma stable for 22 minutes and 17 seconds, a duration that broke the previous record by over 4 minutes. The plasma reached 50 million degrees Celsius, roughly 3 times the temperature at the center of the Sun. This might not sound like much progress to those who do not know about fusion research. After all, The Sun has been maintaining fusion reactions for 4.5 billion years without human help. But creating and controlling a star-like process here on Earth is one of the most difficult challenges in all of science and engineering. Fusion works by forcing atomic nuclei together so tightly that they overcome their natural electrical repulsion and combine, releasing energy in the process. In the Sun, this happens because the star's enormous mass creates crushing gravitational pressure at its core, along with temperatures of 15 million degrees. On Earth, we do not have that gravitational advantage, so we need even higher temperatures to achieve fusion, and we need some way to contain plasma that's hot without it touching any physical surface, since no material can withstand such temperatures without instantly turning into gas. The solution is magnetic confinement. Tokamaks use powerful magnetic fields to create a cage of force that holds the plasma in a donut-shaped region, suspended in a vacuum, never touching the walls. The West reactor's achievement of 22 minutes is important because future fusion power plants will need to operate continuously, not in short bursts. You cannot make electricity cheaply if your reactor has to shut down and restart every few minutes. This record shows that the engineering challenges of continuous operation, managing heat, keeping the plasma stable against changes that can break the magnetic containment, are slowly being solved. The previous record of just over 17 minutes belonged to China's East Tokamak, achieved in January of 2025. This means we have seen two major milestones in plasma duration within weeks of each other. These are not the only fusion breakthroughs happening right now. TEI Technologies, a private fusion company, announced in April 2025 that they had greatly simplified how they form and stabilize their plasma. Their method uses something called a field-reversed configuration, or FRC, a magnetic structure that is smaller than a traditional tokamak. Before, creating an FRC required complex formation sections at each end of the machine, where plasma was generated and then sped up and collided at high speed in the center. TEI figured out how to create, heat, and stabilize an FRC plasma directly in the center of their device, using only neutral beam injection. This removes the need for complex formation hardware. This reduces cost, increases efficiency, and brings them closer to showing they can produce more energy than they used before the end of the decade. Meanwhile, the private fusion sector as a whole is growing quickly. Commonwealth Fusion Systems is building a pilot plant called Spark outside Boston, set to start operating in 2027. Helion has completed initial tests on their latest machine, designed to reach break-even energy production using a different magnetic containment system. General Fusion, based in Canada, is building a demonstration system that uses a completely different approach, mechanically squeezing plasma rather than relying only on magnetic fields. The variety of approaches shows both how difficult the problem is and the understanding that there may be multiple ways to achieve successful fusion energy. In December of 2022, scientists at the National Ignition Facility achieved fusion ignition for the first time. This was a reaction that produced more energy than the lasers used to start it. That was a scientific landmark, proof that controlled fusion is physically possible. But turning that proof into a power plant requires solving countless engineering challenges. Fusion fuel, usually a mix of deuterium and tritium, both types of hydrogen, must be continuously supplied. The neutrons produced by fusion reactions carry enormous energy and make the reactor walls radioactive. So, materials need to withstand years of neutron bombardment without breaking down. The heat generated must be captured efficiently and turned into electricity, and all of this must happen at a cost that can compete with other energy sources. What makes fusion so tempting, despite these challenges, is the promise of nearly limitless clean energy. Deuterium can be taken from seawater, where it exists naturally as one atom in every 6,500 hydrogen atoms. At that concentration, the oceans contain enough deuterium to power human civilization for millions of years. Tritium is rarer and must be made from lithium, but lithium is relatively common. Fusion produces no long-lasting radioactive waste like fission reactors do. It produces no carbon emissions, and a fusion reactor cannot melt down or explode because the plasma is so thin that any disruption simply stops the reaction. The question is no longer if fusion will work, but when it will become practical and economical. Optimists point to the fast progress in both government and private sector projects and suggest we could see the first commercial fusion electricity on the grid by the early 2030s. Skeptics note that fusion has been perpetually 20 years away for the past 60 years, and caution that unexpected problems always arise. But the momentum in 2025 feels different. It is driven by new technology, huge investments, and the urgent need for clean energy sources to deal with climate change. For the first time, it seems likely that a child born today might grow up in a world where fusion power is as common as solar panels or wind turbines. And perhaps that child's generation will use fusion-powered spacecraft to explore the solar system, following the trails of those ancient comets and asteroids, and investigating the planets and moons we have only glimpsed from afar. One of those moons, Mars, continues to surprise us with hints that it once might have supported life. This leads us to leopard spots on Mars. In July of 2024, NASA's Perseverance rover drilled a core sample from a rock nicknamed Chun Falls in Mars's Jezero crater. The rock showed features that mission scientists called the most puzzling, complex, and potentially important they had seen. After a year of strict review by other scientists, the findings were published in the journal Nature in September of 2025. They represent the strongest evidence yet that Mars might have once been home to tiny life forms. The key word there is might, because one of the hardest lessons in astrobiology is that nothing is ever as simple as it first appears. Chun Falls sits in an ancient riverbed within a region Perseverance has been exploring called Bright Angel. Billions of years ago, water flowed through this area, carving channels as it rushed into Jezero crater, which at the time was a lake. The rock itself is sedimentary, made of clay and silt. This is exactly the kind of material that on Earth preserves fossils and chemical traces of ancient life. Perseverance's instruments detected organic carbon, sulfur, oxidized iron, and phosphorus. This combination, on Earth, often indicates living activity. But what really caught scientists' attention were small features they call leopard spots. These are tiny specks rich in iron phosphate and iron sulfide, scattered through the rock like spots on an animal's fur. On Earth, when tiny organisms eat organic matter, they often produce iron phosphate and iron sulfide as waste products. The pattern of these compounds in Chun Falls looks like what we see in Earth rocks that contain fossilized microbial communities. But here is the problem. Chemical processes can also create similar patterns without any living things involved. Hydrothermal processes, hot water activity, volcanic activity, impacts, all of these can create mineral deposits rich in iron. The challenge is telling the difference between origins related to life and non-biological origins, based only on chemistry and texture. This is especially hard when you're doing it remotely with instruments on a rover millions of kilometers away. This uncertainty is why scientists use the term potential biosignature, rather than claiming they have found proof of life. A potential biosignature is a substance or structure that could have come from a living thing, but it needs more information or further study before any conclusion can be reached. It is a careful approach, deliberately cautious, because the claim that we found evidence of extraterrestrial life, even extinct microbial life, is extraordinary and needs extraordinary evidence. The scientific community learned this lesson from past disagreements, like the announcement in 1996 that a Martian meteorite found in Antarctica contained possible fossils of bacteria. That claim could not be definitively confirmed or denied by later research. What makes the Chun Falls finding particularly interesting is the age of the rocks. The Bright Angel Formation is relatively young in geological terms, younger than many of the ancient rocks Perseverance has studied. An earlier idea assumed that signs of ancient life would only be found in the oldest rocks, formed when Mars had a thicker atmosphere and liquid water on its surface. Finding potential biosignatures in younger rocks suggests that Mars might have stayed habitable for longer than previously thought, or that conditions suitable for life returned at later times. Perhaps volcanic activity periodically warmed the planet, melting ice below the surface and creating temporary places where life could survive. The sample, officially named Sapphire Canyon, after a waterfall in the Grand Canyon, is now one of 30 samples Perseverance has collected and stored in sealed titanium tubes. These samples represent different parts of Martian geology, rocks from different eras and environments. Each one was chosen because it might contain clues about Mars' past. The ultimate goal is to return these samples to Earth as part of the Mars Sample Return mission. Although that mission faces big technical and money challenges, Bringing samples back would allow scientists to analyze them with instruments far more advanced than anything we can send to Mars. These instruments can measure the ratios of different atoms, search for amino acids, and examine mineral structures at the atomic level. Until then, the Sapphire Canyon sample sits inside Perseverance, a tiny piece of Mars containing what might be the most important discovery in the history of astrobiology, or might be nothing more than interesting geology. The uncertainty is frustrating, but also exciting. We are living in a time when the question of whether life exists beyond Earth might finally be answered, not through guessing, but through direct observation. Whether that answer comes from Mars, or from the icy moons of Jupiter and Saturn, or from looking at the light from exoplanet atmospheres, the search is moving faster than ever before. It is driven by technologies that did not exist a generation ago. Some of those technologies, especially in artificial intelligence, are advancing so quickly that they are changing many fields at once. Our 7th chapter is about the silicon mind. In 2024, the average company spent $1.9 million on generative AI projects. Yet, less than 30% of AI leaders reported that their CEOs were happy with the return on investment. This difference shows something important about where we are in the AI revolution. The technology works, sometimes amazingly well, but turning that ability into real business value turns out to be harder than the initial hype suggested. 2025 is the year that this reality check is forcing a change. Companies are moving from trying out AI to actually using it for specific tasks. They are moving from asking what AI can do to asking what problems it can truly solve better than existing methods. The capabilities themselves continue to improve at an astonishing rate. In September of 2025, researchers at Microsoft announced a breakthrough in protein simulation using an AI-driven system called AI2BMD. Proteins are the tiny molecular machines of life. They fold into complex 3D shapes that determine what they do. Understanding how proteins fold and interact is vital for finding new drugs, engineering enzymes, and understanding diseases. But simulating protein dynamics has always required a lot of computer power, because proteins are large molecules with thousands of atoms, and their behavior depends on quantum mechanical interactions at the smallest levels. AI2BMD allows researchers to simulate these dynamics with incredible speed and accuracy, potentially speeding up the discovery of new drugs and treatments. This is not the only way AI is changing science. In neuroscience, an AI model called Cell Transformer, developed by researchers at UCSF and the Allen Institute, has created one of the most detailed maps of the mouse brain ever produced. It identified 1 to 300 regions and subregions, including areas that were not known before. The model works by analyzing massive datasets of gene activity in specific locations, basically mapping which genes are active in which cells and where those cells are located. This allows the AI to find patterns and boundaries that human researchers might miss, showing the brain's organization in a level of detail that would take decades to achieve by hand. The same AI techniques can be applied to other organs and tissues, including cancerous tumors, opening new ways to understand disease and develop treatments. Another AI breakthrough came from University College London, where researchers developed an algorithm that can identify different types of brain cells based on their electrical signals with 95% accuracy. For decades, neuroscientists could record the electrical activity of neurons, but they could not tell what type of neuron they were recording from without using genetic markers or staining techniques. This new approach uses AI to recognize subtle patterns in the electrical pulses that different types of neurons produce. It is essentially teaching a machine to read the neural code. The implications for brain-computer interfaces and treatments for brain disorders like epilepsy are significant. However, as the researchers warn, there is still a long way to go before this becomes a practical tool in clinics. But AI is not just speeding up research, it is becoming a part of everyday tools and workflows. In 2025, Gartner predicts that 75% of businesses will move from testing AI to using it fully. This means a huge expansion of data infrastructure and analysis. AI agents, which are self-governing or partly self-governing software programs that can sense their environment, make decisions and take actions, are moving from idea to reality. These are not the chatbots of 5 years ago, which were limited to pre-written answers. These are systems that can handle complex tasks like analyzing legal contracts, managing supply chains, writing and fixing code, and even giving personalized medical advice. The rise of AI agents raises questions that go beyond technology. If an AI agent makes a mistake that causes harm, who is responsible? The developer, the company using it, the user who relied on it? In late 2025, a lawsuit in Colorado highlighted these issues when parents claimed that an AI chatbot had contributed to their teenager's suicide by simulating emotionally manipulative conversations. The case could become very important in deciding who is responsible for AI systems and what moral duties companies have when they create them. As AI becomes more capable and more integrated into sensitive areas like mental health, education, and personal relationships, society will need to deal with questions about trust, accountability, and the proper limits for artificial intelligence. There is also the question of how AI itself will develop. Current large language models are trained on huge amounts of text taken from the internet. They learn patterns in language that allow them to create clear and often useful responses. But they do not understand what they are saying in any deep sense. They lack common sense reasoning, they make factual errors, they can be fooled by tricky inputs, and they sometimes produce outputs that seem confident but are completely wrong. This is a phenomenon called hallucination. The next generation of AI systems will need to address these limits. They will need better reasoning, the ability to check their own outputs, and perhaps some form of understanding that goes beyond just matching patterns. Some researchers believe the way forward is to combine different types of AI, what is called composite AI. Instead of relying on a single large model, you build systems that integrate multiple specialized models, each good at a particular task, along with traditional software and databases. Others think the breakthrough will come from better training methods, or from combining AI more closely with robotics. This would give AI a body and sensory feedback so it can learn about the physical world the way humans do. And there is growing interest in neuromorphic computing, building computer chips that copy the structure of biological brains. This could potentially offer more efficient and capable AI than current methods. Whatever direction AI takes, it is clear that we are still in the early stages of understanding what this technology can and cannot do, and what it means for society. The excitement is justified. The potential is real, but so are the challenges and risks. As we develop more powerful AI, we also need to develop the wisdom to use it responsibly. That same need for wisdom applies to another area where our basic understanding of reality might be changing, the mysterious components that appear to make up most of the universe. We now consider the illusion of darkness. For nearly a century, scientists who study the universe have believed that it is mostly made of things we cannot see. Ordinary matter, the stuff of stars, planets, and people, makes up only about 5% of the universe's total mass and energy. Another 27% is dark matter, which is invisible but can be detected because of its gravitational effects on galaxies. The remaining 68% is dark energy, an even more mysterious force that seems to be speeding up the expansion of the universe. Together, dark matter and dark energy dominate the cosmic budget, shaping the structure and fate of everything that exists. But what if they do not exist at all? In October of 2025, a paper by Rajendra Gupta, a physics professor at the University of Ottawa, suggested a radical alternative. Instead of filling the universe with invisible particles and unexplained energies, Gupta suggests that the fundamental forces of nature, like gravity, are slowly weakening as the universe gets older. If this is true, then the things we attribute to dark matter and dark energy might be illusions. They might be errors from using constant laws of physics to describe a universe where those laws are slowly changing. The idea is both simple and profound. We assume that the strength of gravity today is the same as it was 1 billion years ago, and will be the same 1 billion years from now. But what if that assumption is wrong? What if gravitational pull was slightly stronger in the past and will be slightly weaker in the future? Such a change could make distant galaxies spin faster than we expect based on visible matter alone, making it look like dark matter is present. It could also make the universe's expansion seem to speed up over time, making it look like dark energy is at work. In this model, you do not need strange invisible substances. You just need constants that change over time, a universe where the rules gradually change as space itself evolves. This is not the first time someone has suggested changing our laws of physics to remove the need for dark matter and dark energy. Modified Newtonian dynamics, or EBN, has been around for decades. It can successfully explain how galaxies rotate without using dark matter halos. But Mond struggles to explain observations on larger scales, like how galaxy clusters behave, or the patterns we see in the cosmic microwave background, the leftover glow from the Big Bang. Gupta's approach, which he calls CC plus TL, tries to provide one explanation for both the very large scale, where dark energy seems to operate, and the scale of galaxies, where dark matter seems necessary. By adding a factor that changes with both time and the local density of matter, he can reproduce the observed rotation of galaxies and the accelerated expansion of the universe without adding any new substances. The timing of this idea is interesting because it happens at the same time as other hints that something might be wrong with our standard model of the universe. Data from the Dark Energy Spectroscopic Instrument, or DESI, released in April of 2025, suggests that dark energy may not be constant after all. Instead, it might be weakening over time, changing in ways that the standard model cannot easily explain. If dark energy is changing, then we need to update our theories. And once you start updating, it is worth asking whether dark energy, as we currently understand it, exists at all. Meanwhile, experiments searching for dark matter particles continue to find nothing. The Lux Zeppelin detector, the most sensitive dark matter detector ever built, has been running for years and has found nothing. It has set strict limits on the properties that dark matter particles, if they exist, must have, progressively ruling out vast areas of theoretical possibilities. Each time it finds nothing, the remaining options for what dark matter could be become stranger and less likely. Some physicists are starting to wonder whether we are searching for something that is not there. It is like ancient astronomers adding more and more circles to try to make the Earth-centered model of the solar system work. But giving up on dark matter and dark energy is not easy, because they explain so much. They explain why galaxies rotate the way they do, why galaxy clusters stay together, why gravitational lensing, light bending, happens where it does, why the cosmic microwave background has the pattern of hot and cold spots that we observe. Any alternative theory needs to explain all of these things, at least as well as dark matter and dark energy do, and preferably better. Gupta's model is a step in that direction, but it will need to pass rigorous tests against all the data we have about the universe before it can be seen as a serious contender to the standard model. What makes this debate so fascinating is that it touches on the most fundamental question in science. How do we know what is real? Dark matter and dark energy have never been directly detected. We guess they exist from their gravitational effects, from how visible matter moves, from the structure of space-time. But guessing can be misleading. For centuries, astronomers believed that planets moved in perfect circles because circles were the most perfect shape. The truth turned out to be ellipses, a simpler solution once you stopped assuming perfection. Could we be making a similar mistake now, assuming the universe contains exotic substances, when the reality is that our equations need adjustment? The answer will come from more and better data. The Vera C. Rubin Observatory, expected to begin observations later in 2025 or early 2026, will survey the sky with the largest digital camera ever built. It will image billions of galaxies with amazing detail. The data it collects will test dark matter and dark energy models with a precision that current experiments cannot match. Similarly, the Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will measure the universe's expansion rate and map the distribution of matter on cosmic scales. Between these new instruments and ongoing experiments, the next few years should clarify whether dark matter and dark energy are real, or whether we need a fundamental rethinking of how we understand the universe. Either way, the process reveals something beautiful about science. It is never finished. Every answer opens new questions. Every certainty eventually meets a challenge. And sometimes, the most revolutionary discoveries come not from finding something new, but from realizing that what we thought we knew was incomplete. Let's move on to the space between. While scientists debate the nature of the cosmos and engineers build quantum computers and fusion reactors, another quieter revolution is happening in how we travel beyond Earth's atmosphere. On October 8, 2025, Blue Origin launched its 15th space tourism mission. The passengers experienced a few minutes of weightlessness, saw the curve of the Earth against the blackness of space, and returned safely to the ground. For them, it was likely a life-changing experience. It was the kind of perspective shift that astronauts call the overview effect. For the space industry, it was business as usual. Another successful flight in what is becoming a regular commercial operation. This normalization of access to space feels important when you step back and look at the bigger picture. A generation ago, spaceflight was only for government agencies and professional astronauts. These were people who trained for years and went through tough selection processes. Now, private companies are flying, paying customers. And while the price tag is still too high for most people, costs are dropping as technology improves and competition increases. SpaceX has changed rocket launches with reusable rockets, greatly cutting the cost of putting things into orbit. Blue Origin is working on its own reusable systems. Other companies are developing spaceplanes, orbital hotels, lunar landers, and plans for missions to Mars. The infrastructure being built today is not just for tourism. It is preparing for a future where humanity lives on multiple planets. SpaceX's Starship, the largest and most powerful rocket ever built, is designed to carry cargo and eventually people to the Moon and Mars. NASA's Artemis program plans to return astronauts to the lunar surface. It will establish a lasting presence there to test technologies needed for longer missions. China is building its own space station and has announced plans for a lunar base. India, Japan, and several European countries are developing their own spacefaring capabilities. All of this activity raises questions about what we will do once we get there. Space is not an easy environment. There is no air, no water, extreme temperature changes, radiation from the sun, and cosmic rays. Building habitats that can support human life will require solving problems in life support, farming, manufacturing, and medicine. We will need to get resources from asteroids, the Moon, or Mars itself, because launching everything from Earth is not practical for long-term settlement. We will need energy sources, likely solar power helped by small nuclear reactors, and we will need to address the psychological challenges of being isolated, confined, and far from Earth. But perhaps the biggest question is why we should do this at all. The practical answers include getting resources, making scientific discoveries, and ensuring the long-term survival of humanity by spreading beyond a single planet that is vulnerable to asteroid impacts, supervolcanoes, or other major threats. The more hopeful answers point to human curiosity and the desire to explore. This is the same impulse that sent our ancestors out of Africa to populate every continent, that pushed explorers across oceans, that drives scientists to look ever deeper into the mysteries of nature. Space represents the ultimate frontier, not because it is empty, but because it is vast and largely unknown, full of possibilities we can barely imagine. And space exploration does not happen separately from the science and technology we have been discussing. Quantum computers might one day optimize spacecraft paths or enable new forms of communication across planets. Fusion reactors could provide the power needed for fast propulsion systems that reduce travel time to Mars from months to weeks. AI will be essential for managing the complexity of life support systems, navigating autonomously, and analysing the huge amounts of data collected by sensors. The search for signs of life on Mars or the moons of Jupiter informs how we think about where and how to look for life beyond Earth. Everything connects. The universe is not made of isolated parts, but of relationships, patterns that repeat at different scales, principles that apply everywhere. A comet's chemistry tells us about planet formation. A quantum computer's behaviour reveals fundamental truths about reality. A fusion reactor copies the processes happening in stars. A brain-mapping AI shows how complex things appear from simple rules. And a private spaceflight company makes it a little more possible for humans to become citizens of the solar system, rather than residents of a single planet. These connections matter, because they remind us that progress is not a straight line. It does not happen in one field at a time, neatly separated. It happens through mixing ideas, through ideas developed in one area finding unexpected uses in another. It happens through teams of people from different fields working together on problems too complex for any one perspective to solve alone. The breakthroughs of 2025 in quantum computing, fusion energy, Mars exploration, AI, cosmology, neuroscience, and space access are not separate stories. They are chapters in a larger story about human ability and curiosity. Finally, we reach the horizon. We began with an asteroid that passed unnoticed in the night, and a comet brightening in the October sky. These are two reminders that the universe is dynamic, and that our place in it is both small and significant. We looked at a distant planet forming moons from a disk of gas and dust, a process that echoes how our own moon came to orbit Earth billions of years ago. We saw quantum computers reaching a level of sophistication where they might soon solve problems beyond what regular computers can handle. We also saw fusion reactors keeping plasma stable long enough to hint at a future, powered by the same reactions that light the stars. We examined a rock on Mars that might, just might, contain evidence that life once existed beyond Earth. Although the question remains open, and will likely remain so until we can analyse that rock in laboratories here at home. We watched artificial intelligence map brains, simulate proteins, and raise new questions about independence, responsibility, and what it means to be intelligent. We considered ideas that dark matter and dark energy, the invisible substances thought to dominate the cosmos, might not exist at all, that the universe we think we know might be based on incomplete equations, and we noted that space travel is quietly becoming more accessible, not yet common, but moving in that direction step by step. Each of these developments comes with uncertainty. Quantum computers might hit unexpected problems that delay their practical use. Fusion reactors might prove harder to commercialize than optimists hope. The Martian signs of life might turn out to be geological rather than biological. AI might stop progressing or need breakthroughs we have not yet imagined. Alternative theories of the universe might fail to explain observations as well as dark matter and dark energy do, and space exploration might remain expensive and dangerous, the domain of governments and billionaires rather than ordinary people. But uncertainty is not the same as being pointless. It is the space where discovery happens, where our understanding grows, where we test ideas against reality and change them when they are not quite right. Science is not just a collection of facts, it is a process, a way of asking questions and refining answers. And the questions we are asking now are among the most profound ever posed. What is the universe made of? How did life begin? Can we harness the power of stars? What is consciousness? Are we alone? How do we ensure that the technologies we create benefit rather than harm us? These questions do not have simple answers, and that is okay. If they did, they would not be worth asking. The value lies in the search itself, in the knowledge we gain along the way, in the technologies we invent to explore deeper, in the way our perspective changes as we learn more. 100 years ago, we did not know the universe was expanding. 50 years ago, we had not visited Mars with rovers or discovered planets around other stars. 25 years ago, quantum computers were just interesting lab experiments, and AI could barely recognize handwritten numbers. The pace of change is speeding up, driven by combined advances in computing, materials, instruments, and understanding. What will the next decade bring? If fusion becomes a real business, abundant energy could transform civilization, lifting billions out of poverty and making projects that currently seem impossible, possible. If quantum computers mature, they could speed up drug discovery, material science, and cybersecurity, reshaping industries and global power. If we confirm signs of life on Mars or detect them in the atmosphere of an exoplanet, it would be one of the most important discoveries in human history. It would be proof that life is not unique to Earth. If AI continues to advance, it could become a partner in scientific research, creating ideas, designing experiments, and analysing data at scales beyond human ability. And if space access continues to become more widespread, the resources and knowledge of the solar system could become common human property, available to future generations in ways we can only begin to imagine. But these possibilities also come with risks. Technologies are tools, and tools can be used for good or bad. Quantum computers could break the encryption that protects everything from bank accounts to military communications. Fusion, if turned into a weapon, could create devastation. AI could reinforce biases, eliminate jobs, or be used in ways that make human lives worse rather than better. And space exploration, if done carelessly, could spread contamination, destroy irreplaceable scientific sites, or make inequalities worse. Managing these risks requires more than technical skill. It requires wisdom, ethics, foresight, and a willingness to consider not just what we can do, but what we should do. It requires many different voices in decision-making, transparency about risks and uncertainties, and humility about the limits of our understanding. The scientists and engineers pushing the boundaries of knowledge are very aware of these responsibilities, even if public discussion sometimes treats technology as either a savior or a threat, with no middle ground. The truth is more complex. Technology is neither good nor bad in itself. it increases human intentions and abilities. In the right hands, with the right goals, it can solve problems, reduce suffering, and expand possibilities. In the wrong hands, or with short-sighted goals, it can cause harm. The challenge is to build systems, institutions, and cultures that aim for the former and avoid the latter, and that challenge belongs to all of us, not just to scientists and policymakers. So, here we are in October of 2025, watching comets brighten, reading about quantum entanglement, learning of plasma records and potential signs of life. The universe continues its ancient dance. Stars forming and dying, galaxies colliding, comets plunging towards the sun, moons forming from dusty disks. Life, at least on one small blue world, has learned to look outward and ask questions. It has learned to build tools that extend our senses and understanding, to dream of futures where the limits of what is possible expand beyond recognition. Thank you for joining me on this journey through the latest discoveries and breakthroughs. If you enjoyed this exploration, consider leaving a like and subscribing to stay connected as science continues to reveal the universe's secrets. The work of understanding our cosmos never stops, and every answer we find opens doors to new mysteries waiting just beyond the horizon. As always, all information shared here is for educational purposes. It is based on current research and understanding, which continues to evolve. Keep looking up, keep asking questions, and remember that we are all part of this grand unfolding story. Until next time, wherever you're listening from, whatever time it is, good night.